Welcome to my channel. I'm Zhang Jingxu. Let's look at the problem 39 in chapter 28. Chapter 28 is about sources of magnetic fields. So there we have non-conducting disks, right? And we know it's rotated with angular velocity omega. We need to find its magnetic dipole moment and magnetic field at a distance x from its center. So how can we do that? So for first one, we can consider this stick be split by a small fraction of the zinc rings, right? The zinc ring, the width is dr, the distance from this ring to the center is r. So after we split it, we can say, can you find the magnetic dipole moment for this ring? Yes. So easy, right? Just get the current di times A. A is the magnetic is the cross-sectional areas. It's easy. By this one, the di, how can we get it? That is the current rotate. So can you find the di? Yes. So di we can consider is a charge divided by a certain time, right? So the charge in this case, we can consider the charge on this small ring is dq, and the time taken is 1 period. So when this dq divided by period can write as 2 pi divided by omega, right? So now we can get the di as a frequency. So 1 over t as a frequency. So omega divided by 2 pi times dq. And this dq is charge on this small ring. So we can use the density of this charge, the charge density times the cross-sectional areas for this ring, right? So charge density is q divided by pi squared, and then the cross areas is 2 pi r times dr, 2 pi r times dr. So you reorganize it, you get a function look like this one, and input di inside, reorganize it, you get the function for d mu. That is the magnetic dipole moment for a small ring, right? Now you want to know the magnetic dipole moment for this disk. So we can do the integral from 0 to r. And then we get the function look like this one. The second part asks you to find the magnetic dipole or the magnetic field at a distance x from its center. So let's say it's there. How can you get it? And very likely we do the same thing. We can consider that the small disk can be split by small fractions, right? So this fraction is a zinc ring. Can you find the magnetic field for a ring a distance x from the center? Yes, this one, right? You can check your textbook for previous works, and then you can get it there. And then the next one, and we know this is magnetic field for this small ring, right? We need to do the integral for it. But there, we need to solve the term the current on this small ring first. As we talk as the previous, right? We can use the charge on this small ring divided by the period. So we get it there. This is frequency times the dq. And then this dq on this charge on the small ring is used the charge density times 2 pi r dr. Reorganize it, you get it there. And input the di inside, you get it there. Right? This is magnetic field for the small ring. Now we do integral from 0 to r. You get the answer there. So now we are done with the magnetic field B at there, right? The next one tell you, how about the x is much larger than r? So how can you solve it? So now there, how can you solve it? This is we just get it, right? When x is much larger than r, that means the r divided by the x is much larger than, much smaller than 1, right? It's almost 0. So now from this equation, we can divide the 2x squared at upper side and the lower side. Look like this one. Do you agree? Just for this term. And for this term, you can do the tiny expansion. Look like this one, right? And then we just keep the first term and then ignore the more terms, right? And then we find we can get the first term look like this one. Simplify it, you get the answer there. This is exactly the magnetic field on the axis of a dipole, magnetic dipole, right? We learned in this equation. Thank you.